of the substances that surround us, such as sugar, salt, or gemstones, are solid crystals. They are substances whose components, atoms or molecules, fit together in an orderly fashion, following a pattern that is repeated in space. When the units that form the crystalline network are also a series of atoms with a defined structure, we are talking about molecular crystals. The properties of any material formed by a molecular crystal depends on the molecules that comprise it, but also on the way in which these are organized. Thus, equal groups of molecules may present different properties depending on the crystal order they adopt. Scientists use different experimental techniques to know how the crystals are organized. One of the main techniques uses high-frequency electromagnetic radiation, and it is called X-ray diffraction crystallography. Humidity is one of the most decisive conditions in the formation and growth of the crystals that make up the materials. Here we have a type of cement called Portland cement that chemically reacts with water. At the Materials Science Institute of Aragón, researchers from the M4 group are working on the design of new strategies to obtain molecular crystals that permit access to materials with new structures and singular properties. To do this, they modify the conditions that surround the crystals, humidity, temperature and chemical environment, to obtain controlled changes in the crystalline structure. Mankind has been applying hydration and dehydration processes to change the properties of materials since antiquity. These processes can also be used with crystals so that certain crystals in certain conditions can incorporate molecules of water into their structure or eliminate them, radically modifying their properties.
In our group, we work on the synthesis of new solid-state materials based on molecules that have a cube-shaped core and which have magnetic properties. At the same time, at the periphery of this fragment, we put molecular hooks so that the fragments can be joined together into more extensive molecules, polymers, which have regular shapes and higher or lower symmetry. So this way we have at our disposition modular building blocks for constructing molecular solids with properties that we can vary. When we dehydrate a crystal formed by the polymer of molecular magnets, we're removing water molecules that interact with the atoms of the polymer, which as a result lose some of their stability. In order to achieve a newly stable arrangement, these atoms form new bonds with other atoms, producing a cross-linking of the polymer chains, which in turn gives a two-dimensional polymer of molecular magnets. In addition, we've discovered that if we control the hydration conditions in a specific manner, it's possible to form a water wire that conducts electric charge in the form of protons within a molecular crystal without the need for channels within the solid.
This discovery opens up the possibility of designing a new family of electric proton conductors, applying the most modern energy production and transformation technologies.
The most immediate application of these proton conductors would be in hydrogen fuel cells. Hydrogen fuel cells need proton conductors, usually in the form of a membrane, to complete their internal circuits. At present, there's a lot of interest in hydrogen fuel cells because they offer a clean and efficient source of energy.
When water is added to the Portland cement, a chemical reaction takes place that makes the structure become much more resistant, at the same time as, on controlling the humidity in the formation of crystals, this increases stability. The use of sophisticated crystallographic characterization techniques such as the X-ray diffraction equipment at the Materials Science Institute of Aragon or the diffraction of neutrons at the facilities of the L'Or-Longuevin Institute of Grenoble, combined with the new molecular crystal design strategies, allow this group to study the materials which may, in the near future, help provide answers to different technological challenges.